Okay, so last class we talked about why gradient descent works, the kind of rate it gets, and then we started digging into how to boost the speed of gradient descent by adding a momentum term, right? So trying to keep track of all of the past gradients. And one intuition to keep in mind is basically what momentum allows you to do is if your gradients are all kind of pointing in some direction, then even if your step size is small to begin with, they kind of build up uh, higher magnitude as you go along. Okay, so that's what the momentum term allows you to do. And then we also saw Nesterov's acceleration, which is kind of similar intuition, but you just do like a look ahead plus momentum, meaning you first take the momentum step and then compute the gradient, a small change. And we said that for quadratic functions, heavy ball is as good as it gets. For general convex functions, which are smooth, Nesterov's is as good as it gets, and that's pretty much the only thing. Okay. So today, what I'll do first is maybe walk through a very concrete example, which is again going to be least squares regression. And after that, we'll see what are other challenges with gradient descent. As it is, GD is a kind of minimalist method, can apply to any loss function as long as you can compute the gradient. But sometimes even that is too expensive, okay, too much to hope for. So what do you do in that scenario? Okay, that's what we're going to talk about. All right. So let's just work a little bit on what these algorithms would do in the case of least squares regression. Okay, as I said, maybe in the beginning, this is going to be a running example for us. So LSR. And just to recall, here we have a data set, which is x1, y1, x2, y2, so on. Okay. And then we have predictors, right? And what is our class of predictors in least squares regression? Is just a class of linear functions, right? So, given parameters theta, the corresponding predictor is just going to be this interval, right? And the loss function that we use to set up the empirical disk minimization problem is just a minus b whole square. Okay. So if you were to write it down more concretely, we would get okay. So every data point xi, compute the inner product with your weight parameters theta, and then compare how close you are to the expected number from your data set. Okay, and then you average it across all of the things. And again, calculus 101, you can compute the gradient exactly by the chain rule. And this is just 1 over n times the gradient of the individual terms, which is this. Okay. So the gradient of a squared is 2 times a, that's this part. And then you have to compute the gradient of what is inside, and that is just it. Okay. All right. And we can also have a matrix view of least squares regression. And this is quite useful when you're actually going to implement it. You think of your data set itself as a matrix, and then your gradient computation and everything becomes much faster. For example, first going back to the loss function, I can think of it as this, okay, which is the squared norm of a vector, which is going to be the following. So imagine I write down a matrix where the rows are my data points, x1 through xn, and I have this theta vector here. That's my parameters, and then I have the corresponding desired labels, y1, y2, all the way up to y. Okay. So this is what I have. And if I call this matrix X and this as vector Y, then this is just the norm square of the vector X times theta minus 1. All right. And finally, you can rewrite the gradient also. So let's recall we had this nice explicit formula for the gradient. Okay. And you can think of this as 2 by n times okay, so if you want to write down the gradient itself also as a matrix, you can compute it using matrix vector multiplication. Okay. If you were to write it up in any Python, any such program, this would be much faster than writing a for loop. Okay, that's just how the languages are optimized. All right. So even for this example, what is the cost of computing the gradient? So in gradient descent, the only thing that we need is to compute the gradient. But how costly is it to compute the gradient? So how costly is GD per iteration? So a single iteration of gradient descent, how much time would this take here? Any guesses? So let's say we're working in d-dimensional space and you have n featured examples. So what would be the cost of GD per iteration? No answers? So how long would it take to compute the gradient if I'm interested, if I have a d-dimensional problem and n examples? N times t. Thank you. All right. So basically, for each thing here, we have to compute a d-dimensional inner product. So this is like O of d time per inner product, right? And we have, once I compute this inner product, I have to multiply this number with a vector again, which is d-dimensional. That's another O of d time. And then I have to add up these n vectors. Okay. So we have O of nd time per iteration. Okay. And now so we want to solve, if you want to solve VRM problems using gradient descent, then even for the special case of least squares regression, we are spending n times d time per iteration. And if you think about it, this can be very prohibitive when your data sets are huge. Okay? We think GD is simple, but even that can be too expensive. Okay. And the same thing happens for general ERM problems, right? So if I have a general ERM problem, I have something like this, right? So this is my structure of the loss function. Okay, so I have some hypothesis class parameterized by some parameters theta, evaluated at my label example xi, and I'm comparing how close is that prediction to the label yi, right? And if I want to run gradient descent, I need to be able to compute the gradient, which by chain rule, once again comes out to be something like the derivative of the loss function with respect to the first coordinate times the gradient of h theta of xi. Okay. So once again, this is going to be a d-dimensional vector if you have d parameters, right? So if I have a billion parameter network, then I have billion parameters here. And then if I have n examples, then it's like n times d. That seems to be the bare minimum for computing the gradient. Okay. So if we have d parameters, then each gradient computation is, at least O of n d. It could be even worse. Maybe the gradient is even more complicated, but at the very least, you have to spend d time because there are d parameters, and then you have to add it up over this n examples, which gives n. They're very, very expensive. Okay, in some regime of parameters. Okay. So more concretely, suppose we have a database of million images, right? So n is like 10 to the 6. And maybe our images are just 250 by 250 pixel, right? So what does this mean? Our D is 250 times 250. Every pixel is like a feature, it's like a coordinate. So the cost per iteration is 10 to the 6 times 250 times 250. And this is just the cost of the time. And you can also be in scenarios where the memory usage could be all over the place. Okay, so hold on. Let's see where I can. Okay.
Professor,
Yeah.
can I ask a question?
Uh, sure.
Yeah, do you mind explaining how you got O of ND again? Also, what is the subscript next to L prime when
Okay.
you're calculating? Thank you.
Okay. One second. All right. I think we are good. Okay. So. All right. So the question was, why is it n times t? And the reason is that you have d coordinates in this vector, and you have to add it up n times. So each addition takes d time. So, and you have n additions, so it becomes n times t. All right. And this is the, one second. Yeah, and here is just the derivative and like the first coordinate. So if you think of this as A and B, I'm only taking the derivative of L, the partial derivative of L with respect to the first coordinate. Okay. So this is how we compute the gradient for any function which is coming from empirical risk minimization. All right. Okay. So, the cost per iteration is very high. And this is not even including things like, maybe your data set is spread over multiple servers. Then you have to make a pass over everything and then come back. Even the memory footprint could be very expensive. Okay. And this is a significant problem. To summarize, the cost per iteration is too expensive. Right. So what can we do to mitigate this? Any suggestions? What can we do to get around this issue? Okay, even running gradient descent, which seems like the simplest possible algorithm in the context of how we access the function L, that seems too expensive. So what can we do then? That's a good, suggestion. In fact, there are, people do that in some cases. Those are kind of called zeroth order methods. Okay, so first order methods meant I'm assuming I can compute the gradient, right? And the suggestion is, gradient is defined as the limit, right? The gradient of a point. Just if you think of the derivative, let's say f is a univariate function. And then just to take an example, f prime of x is really the limit theta goes to 0 or h goes to 0 of f of x plus h minus f of x divided by h. Okay, the rate of change of f around the point. Okay, and zeroth order methods mean you cannot even compute the gradient, but I can evaluate the function at any point. Right. So one thing you can do is maybe take some small perturbation and compute this gap, compute this ratio, and use that as an approximation of it. All right. But this still means that you have to compute the function multiple times, and especially in high dimensions, it can still be tricky. Okay, I had to do this in multiple directions, and also it's kind of not. This is used sometimes, but it's not very rigorous. Okay, so how small this perturbation needs to be, it really depends on where you are and what function you're using, and so on. One of the places where this is used is to do attacks on networks and so on, but let's not get into that. All right. So what else can we do? Yeah. So basically, the whole issue is that we are not able to compute the gradient. So you can ask, maybe how robust is GD or gradient descent and its variance to dealing with approximations? Okay. So you're kind of, pushing this even one step further. I'm saying I don't even know how to compute the gradient exactly, but maybe I have some fast ways to get good approximations of the gradient. Okay. So And this will eventually lead to a trade-off. But it's a trade-off maybe that we will be happy with. Okay, so we are going to settle for some approximations of the gradient, which means that, maybe you'll end up using more iterations, more number of rounds than GD, or you forget, even the accelerated ones even. But it's still good enough to give you some savings. Okay, so this is a trade-off that might be okay for us, right? Okay. So the abstraction that we will use and is very helpful actually is the following. That's weird. Okay, so we have a function. All right. And we need gradient of f at a point x. So we don't have access to the gradient, but what we will assume is that I have some approximator to the gradient. Okay. In fact, let's say I have an estimator for the gradient, meaning we have an estimator. Okay. So we should really think of it as, some kind of function again, which is at a point x. Right? So just as gradient depends on where you are, to think of gx as a function which depends on where, on x, with the property that it's like a randomized function. It's an approximator. It's an estimator for what the gradient is going to be. For the gradient gx, meaning the expected value of the estimator is exactly the gradient. Okay. All right, any questions about the definition? So for every point, I have some way to estimate the gradient. Let's not question where this estimator comes from, but given this estimator, we're just going to use this as the surrogate for gradient. That's a very simple trick. And so let me. Something is wrong. Breaking up. Hold on. Okay. And this leads to what's called the stochastic gradient descent algorithm. Okay, or SGD. All right. And so what is SGD? It's basically GD, but you replace gradient with whatever estimator you have for the gradient. So, you start at some point, x0, and for I equals 1 to so on, you set xi plus 1, or xi equals xi minus 1, eta times. Okay, so you have some step size, and we're just using our estimator for the gradient at that point instead of the grade. That's the only change. All right. Okay. So before going on, we can of course get different kinds of estimators. And let's just talk about quality of estimators. How do you measure the quality of an estimator? What would make one estimator better compared to another estimator? Any suggestions? Yeah. Well, we're assuming it's no bias already. You're absolutely right, but we're already assuming that there is no bias in the estimator, in that the expected value is exactly the grade. Some cases, this might already be too strong an assumption, but let's at least work with this for now. Even given this, unbiased estimators, how would you distinguish one over the other? Yeah. Variance, lower variance is better, right? So for example, let's say, I can say, if my random variable takes value 2 with probability half, 0 with probability half, then the expected value is 1, right? So let's say this is my variable y, expectation of y equals 1. And, maybe I have another random variable, which is like, let's say, 1000 with probability 1/1000, 0 with probability 999,000. Okay. Now the expected value is still 1. Okay. Which is better between the two? The first one. That's a much better estimate, right? And the way we measure, quality is by looking at the variance, right? And the same way, you can generalize the notion of variance to vectors as well. So just to recall, I don't know what's happening to it. If x is a, wait, I'm not choose x, if y is a real valued random variable, then the variance of y is defined as expectation of y minus expectation. Okay. So the squared distance from the expected value in expectation. Okay. Another way to write this is that this is just right. And you can also define a similar quantity for vector value random variables. So what should the definition for vector value random variables be? What would be like an analogous notion for variance? We want a single number to tell us, okay, how good an estimator it is. So how should I change this formula to get to the vector value case? Any suggestions?
Inner product.
Yeah, exactly, right? Just inner product or, the L2 norm really. Okay, so either one, it's the same formula. Okay, so we're measuring the distance between your typical realization from the mean and looking at the norms. So whenever this is small, that's a better estimator in high dimensional spaces. Okay, so just keep this variance in mind, and that's going to be our measure of how good an estimator you have. If I can compute the gradient exactly, then the variance will be 0. I have a perfect estimator, so there's no variance at all. Lower the variance, the better it is for us. Okay, so now let's go back to ERM. Then my gradient is this guy. Sorry, this was my loss function. And the exact expression for the gradient was this. Right. So you can come with all kinds of estimators, but what's a simple estimator for the gradient given this form? Yeah. Yeah.
What is the subscript?
Oh, this one is meant to say I'm only taking the derivative with respect to the first coordinate. Right. So think of L as a function on the two coordinates, a comma b. It's a bivariate function, but I'm only taking its, kind of the partial derivative with respect to the first coordinate. Okay. Because that's the only one that depends on theta. When you apply the chain rule, I'm going to get only the derivative with respect to the first coordinate. Okay.
Professor,
Yeah.
for the vector valued random variable x on the right hand side of, should it
yeah.
be x? Thank
It
you.
should be X. Thank you.
Thank you.
Okay. All right. So what would be an estimator for this? Any suggestions? Well, you can come with many estimators, but one simple estimator, which is very useful, is to, we really have like 1/n times n sample points. Okay. So one estimator is to just pick a point at random. Right? So pick I uniformly at random from 1 to. Okay. So pick a random example and compute this quantity that is going to be our estimator for the grade. Okay. And it's not easy to calculate. It's not hard to calculate that. If I look at the expected value here, this is exactly going to be 1/n times okay. So this is an estimator that works for any ERM problem. All right. Okay. And there's also a generalization of this, which, is one that gets used a lot, which is called the mini batch estimator. Where instead of picking like a single point, I can, maybe my budget allows for picking 10 points. I can't do a pass through the entire data set, but maybe my computational budget per iteration allows me to do 10 times 10 points or 20 points or something like that. And here, when I mean budget, it need not just be the time. There could also be memory constraints. There could also be constraints about, parallelization and so on. Okay. So we pick k random indices. And then I consider the average here. Right, so just pick k random points, compute this quantity at k different points and average. Yes, k increases, your cost is increasing, but intuitively your estimator should be getting better and better. Okay. So what did we win here? What's the cost of computing g theta? So what's the cost of computing this estimator now? We just have to do one evaluation, right? So that's basically O of d, which is great. We're saying we dropped from n times d to O of d. That's the biggest win. Okay. And you also have the cost of the mini batch is O of k times. Okay, instead of n times d, if you pick k points, it's going to be like k times. All right. And in practice, actually what you do mainly due to memory and parallelization constraints is you don't pick a random point every time you want to do an iteration. Okay, that's a little bit too expensive because you have to move around the data sets too much. And indexing into a matrix is more expensive as you go along. So what you do instead is you order all of the points in a random order. Okay, meaning permute all of the points in some random way. So you get xi1, yi1, xi2, yi2, and so on. You permute them once and then keep it like that. Okay, and go sequentially through this order. Okay, so maybe I end up with something like x100, y100 first. And then maybe I had, x17, y17. Maybe then I had x51, y51, and so on. Okay, so I just put them all in the random order. And then I use my estimator, just for this point, and then this point, and then this point, and so on. Or if I'm using mini batch estimator, then I will group this, every 20 going to one mini batch. The first 20 is 1, the next 20 is 1, the next 20 is 1, and so on. Instead of sampling 20 at random every time, I just reorder once and then make one pass through everything. Typically, it's not done because it is expensive to move things around. Okay, but there can be use cases. Okay, so the only, I think there would not be a significant computational benefit to doing that, at least convergence wise. But reordering is also an expensive operation. Does it make sense? Because if you have to move around things, then it's yeah, but again, if picking 10 things at random is much more expensive. It's like writing a for loop versus matrix vector multiplication. So what you do when you do it this way is I permute once, then I have this giant matrix, and then I first look at only like the first 20 rows and multiply, next 20 rows and multiply, next 20 rows and multiply, right? That's much faster than I have a matrix, I have to look at like, the 11th row, 17th row, 21st row, and so on. Okay. So in fact, the term that people use is one pass is called an epoch. Okay. So you do this random ordering, go through one epoch, meaning, whatever batch size you pick, 20, 20, 20, or 1, 1, 1, 1, and so on. You make one pass with the entire data set. That's one epoch. And then you start from the beginning again. Okay. And another advantage of this is if after you permute, things are across very different servers, you don't have to go back and forth. Whereas if I'm picking points at random, I might have to go back and forth across the different servers because your data set itself might be stored across different servers. Okay. So all of these practical considerations kind of, they're very important things, but we're not going to focus too much. But at the very least, they're reasonably automated at this point. Okay. Does it make sense? Okay. Any other questions?
Professor, can you hear us? Hello. Professor?
Yeah.
Oh yeah. I wonder if you can give me like an intuition behind how to prove the mini batch estimator's expectation is actually
For the mini batch?
yes.
That's a good question. So how would you prove that mini batch estimator is also an unbiased estimator? So one way to prove it is to basically argue that each individual summand has the right expectation. Okay. So you're basically using like linearity of expectation. So the first index is like one instance of the usual estimator. So that has the right expectation. And then I'm taking an average of different estimators, which are all good. So the final result will also be good.
Got you. Thank you.
Yeah. All right. So how good of an estimator do you need? The next question is, okay, we were driven to using estimators because of computational reasons. But how good of an estimator do you really need to get some convergence? We need to understand. So we already know GD works reasonably okay, but how good of an estimator do you need? You can ask two things. One, when can I get good convergence guarantees? Or if I view GD as my holy grail, how good of an estimator do I need to kind of match the performance of GD? Okay. You can also ask, which in fact happens in some applications. SGD can do better than gradient descent for non-convex functions because of some, other reasons. Okay. All right. So but once again, just like for convex function, for gradient descent, let's view convex functions as our test bed. And what we will show is the following. So if I have a function which is beta smooth, a nice class of functions and convex, and suppose we have an estimator for gradients with variance at most sigma square. Okay. So I have an estimator, and the assumption we're going to make is that the variance of this estimator is at most sigma square. You could have gotten this estimator by mini batch, by a single point, or any other means. Maybe you have some crazy hashing or projection technique, which is giving an estimator. It's all fine. Okay. We don't care particularly about the form of the estimator, but only about the variance of the estimator. All right. Then and here you'll see that, in fact, the analysis suggests a twist, which is important in some applications. Okay. then like for gradient descent, we said after k iterations, you're close to the optimum in some sense. You're close with error, something like 1/k. Okay. So here, you're also going to be close in expectation. Remember, this is all a randomized algorithm because at every point we have some randomness and maybe you're very unlucky and your gradient is way off. Okay, then your entire path will be very way off. Okay. But in expectation, you are going to be somewhat close to the optimal value. But how close? It depends on you have kind of the same term as before, right? We had this equation. This was what we had for gradient descent, right? So if you ran for k iterations, the error was like 1/k. But now we also have the step size thing. This is exactly what you have for stochastic gradient descent too, but you have some loss which comes from the variance in your estimator. If your estimator is terrible, you cannot expect to match this, right? So how does it show up? It shows up in a very clean way, actually. It's just eta times sigma squared by. Okay. So what is it saying? It's saying if you choose a step size to be very small, then you end up having to take many iterations. But then the cost of having the variance is going to be small. So you have to balance these two. If you have a very bad estimator, then you can still do something, but that means you have to be much more conservative in the step size. Your eta has to be much, much smaller to account for the noise. Okay, this is something I mentioned last lecture too, that when you have noise, you have to be even more conservative in your step size. Because one wrong step can send you all the way back. Okay, so that's the first change. Yeah. Exactly, that's what I'm going to get to next. So the X bar here is the other change. So unlike gradient descent, SGD need not be monotone, even for convex functions. Sometimes you might take a step which is kind of taking you backwards, which can increase your loss function. Okay, because there is randomness. Sometimes you have an estimator, but the gradient is pointing completely in the wrong direction. That can happen. The estimator is pointing in the wrong direction. That can happen, right? So X bar is the average of all of the iterations so far. Okay. So in GD, the guarantee was that F evaluated on the last point, wherever I ended up, is going to be close to the optimum. For SGD, it's F evaluated on the average. In practice, you don't take the average of the entire trajectory, like trajectory meaning all of the points that you visited in your gradient descent or SGD version. You might take the average across the last 10 iterations or 20 iterations, or keep track of the best possible point among all of the things that you see. Either one would work. Okay, does that make sense? So these are the changes from this. Or you can set X bar to be, whatever point gives you the smallest possible loss among everything that you've seen so far. And this is because SGD is not monotone. For gradient descent, this minimum is just going to be the last point, as long as your step size is not big, too big. And here, even if the step size is small, sometimes you can take an opposite step because of the variance. Okay. And you can, you can set the parameter eta in some way. There are various ways to do it, but the best possible choice, even the best possible choice, only gives you the following. Okay, as a corollary, So by choosing eta, which is less than or equal to 1 over beta, and as I said, if you choose a very small eta, the penalty for the variance decreases, but then the error here blows up. Okay. So to balance it, you kind of set the two to be equal, then you get eta squared equals something. So eta should be like 1 over root k. Okay. So you end up with the following guarantee. Okay, so the best you can do is the square root k. And this happens if we set eta to be so gradient descent has a convergence of 1 over k. SGD has a convergence of 1 over square root. And as I said, this is because this expression is minimized when I said eta to be this value. Okay. Of course, we don't know these things exactly, but there are various tricks to kind of set eta appropriately, even though you don't know these values, and get this 1 over square root k. All right. Okay. To summarize, so let's say I have, f is, once, beta smooth convex. And then if I only focus on the number of iterations needed to get some error, epsilon, think of variance as being constant, the norm as being constant, beta as being constant, like they're all 1 or something. Then GD needs O of 1 over epsilon iterations to get error epsilon. And actually, let's say SGD needs 1 over epsilon squared. GD is O of 1 over epsilon. And NAGD is O of 1 over squared. Okay. So for example, if I set epsilon to be 0.01, then this requires 10,000 iterations, roughly. This is 100 iterations, and this is 10 iterations.
Standard gradient descent. Yes. Faster.
For you mean stochastic gradient descent?
See?
For this one,
Oh,
yeah, it can be faster than SGD for sure.
Say even with the overhead of epsilon is.
Yeah, it depends on the overhead, right? You can think this is bad, but then the cost per iteration is much smaller, right? Is that what you're asking? Yeah. Does it make sense?
So SVG has a substantially cost per duration.
Exactly, right? But again, substantially, I would say in many cases, this is a winning trade-off, right? Because let's say I have 1 million data points, then I have to do maybe 10,000 rounds versus 100 rounds, but I saved 1 million costs per round. So the savings per round are going to trump the cost per iteration, the total number of iterations that you do. Okay. So depending on the dimension of the problem and kind of, the variance, the norm bounds and so on, SGD can actually be a better trade-off. All right. You had a question? Yeah. K is the number of iterations that we've done, number of steps, right? So after K steps, we have like a loss of 1/8 of K, but I can't use the last iteration just like, I can't just use the last iteration like I did for GD. Okay. There are convex functions where if I just use the last iteration, SGD will do terribly. Because of the randomness, sometimes, you can deviate a little bit, and it can hurt you. But on average, you should do okay. That's what the theory suggests. And even in practice, you observe it. And typically what you do is either implement this, take the best set of parameters that you've seen so far, right, across the K iterations, because sometimes, I find something very good, but because of the randomness, I might end up somewhere else. But the fact that I've seen something good, I might just keep that in mind. This has some extra memory cost, so sometimes you don't use this, or you can do something in between, like, maybe I average just the last 10 iterations instead of only focusing on one. Each, just F is my cost function, right? Whatever I'm trying to minimize. I start with x0, and then I go to x1, then I go to x2, so on up to xk. Oh, okay. So remember the way we are doing it, you can apply SGD to ERM, but in general, it's an algorithm that you can use to minimize any loss function. It's not specifically tailored for ERM, right? So F is my cost function that I'm trying to minimize, and I'm looking at points x0, x1 through xk, which are in this domain RD. Okay. In the K, when I apply this to ERM, these x's are like the thetas. Maybe that's the confusing part. Right? Okay, so we can apply GD, SGD, NAGD to ERM, but they're not only bound. They're not restricted to only that. Okay, they are functions that you can use to minimize any loss function, any cost function. Okay. Yeah, exactly. In the case of ERM, we have kind of, just from their formulation, there's a natural estimator that you can come up with. But even for many different cases, like you can come up with estimators for the gradient, even when the function that you're trying to optimize doesn't have anything to do with it. Okay. Mm-hmm. Right, because previous ones were deterministic, right? There was no randomness, but now there is randomness that's coming from the estimators. So this expectation is over whatever randomness that's in the estimators. Okay. To properly define it, you have to do like some sigma algebra and so on, but let's not worry about that. Basically, what we're saying is given every point x, I have an estimator for the gradient. And that's what I'm taking expectation. Okay. Any questions? Any other questions? All right. So you have this kind of trade-off in terms of, how many steps you would need to get a F7. And in fact, when you implement it, you see this clearly. But depending on the size of the problem, this might still be a winning trade-off. And typically it is. Yeah. That's an excellent question. So usually it does give you significant improvement in practice, but in general, okay, so like, for first order methods, we said Nesterov can get this acceleration, like 1/k² is the best, okay? But unfortunately, you can actually show that there are convex smooth functions where you cannot get any more acceleration, right? So momentum does not help in general. Even look ahead plus momentum would not help. Okay. So, it's practice, typically it makes a difference, but there are examples which are a little bit more less common, fortunately for us, where momentum doesn't help at all. So this, I should say, remark okay, so if you only have access to estimators, then the rate of SGD is the best you can get, in general. In practice, people try momentum and it does give you some help. But as I said, for something like NAGD, you have to be much more conservative when there is noise, right? So you don't want to you have randomness in the thing, and momentum just means that you're adding up all of the previous gradients. So if they're pointing in some direction, you want to aggregate it. But if there's noise, and sometimes if you take a wrong step somewhere, it might get amplified more and more and more, which can really blow up in your faces. Okay. So, for first order methods where I only have access to the estimate, to have an estimator access to the gradient, SGD is the best possible. That's a complicated theorem to prove, but that's no. Yeah. I would say SGD would be better than GD, and either would be better than acceleration. You can use acceleration still, but you have to be more conservative. In the step sizes and how much importance you give to the momentum and so on. SGD is more robust, actually. And yeah, it's a very good question. And the intuition is that somehow when your function is not convex, for example, what happens is sometimes, like imagine I am like at a saddle point. Okay. Or actually think of it this way, right? So this is my function. Now, when I'm here, for example, gradient descent is completely stuck, right? Because the gradient is 0. It thinks you have reached the optimum, right? Whereas if I have an estimator, then with some probability, it's going to push me out, right? So sometimes randomness is to our advantage. That's the point. And especially in high dimensions, you might have the saddle points where randomness can throw you out of the saddle points, which are problematic. Like, you instead of getting stuck there all the time, at least there's some chance, maybe 0.1% chance or 10% chance that you actually go out of this bad local. Okay. And that really does happen in practice, especially when your landscape is very complex. So that's one reason why noisy gradient methods or SGD can do better than gradients. Okay. Yeah. Because, so let's see, where did it go? Yeah, here. I'm starting at some point, and then the step I take, there's randomness in it, right? Because I'm using a gradient estimator. If I run the algorithm a second time, I might not end up with the same point. So just imagine I ran the algorithm like 1,000 times, and then I average this expression.
is expected value.
No. That's an like x bar itself is like f of this guy, but I'm saying I'm computing across the different runs of the algorithm. Right. So how do you come? I have a random variable. So this f of x bar is not deterministic. That's a random variable. It depends on what point I actually saw in my estimator, right? And the expected value of that is reasonably okay. Okay, you can also show the variance of this. You can compute the variance. You can show tail bounds, and you can do all of that as well. But just the expected value being good is a good indicator that SGD is a meaningful algorithm to use. Okay. All right. So, let's prove this theorem for SGD. And the proof is actually very close to what we already did. The first thing is some kind of approximate monotonicity property of gradient descent, of SGD, okay, of stochastic gradient descent. So what does this mean? So approximate monotonicity of SGD. Okay. So for gradient descent, we said that as long as my step size was small enough, my next iterate is not going to be worse than where I started. In fact, we said something like this. Okay, so this was the monotonicity property that we showed for any function f that was beta smooth. But as long as the step size was small, gradient descent will only improve the value. Okay. For SGD, you get a very similar statement. First, you have to put an expectation here because it's a randomized process now. And if your variance is very bad, you might get a violation. Okay. So you're basically monotone up to this perturbation term, is eta times sigma squared by 2. Okay. Does it make sense? You might increase a little bit depending on whatever the sigma is. If your variance is very high, sometimes I might go up. Yeah. Yes. Yeah. Really, as I said, if you want to define it formally, you have to define the sigma algebra and so on. But let me just put a single expectation here. Okay. All right. And the proof of this is again just doing the same calculations really, but you just have to do use the fact that your update is only correct in the expectation of your update is the grade. Okay, the same calculations with the expectations really. So let's recall the smoothness upper bound. And what we have is xi plus 1 equals xi minus eta times g, where g is our estimator. this equals the gradient. Okay, so this is the smoothness up. In the case of gradient descent, we just substituted xi plus 1 minus xi is negative of the gradient, and then you simplified it and we got it, right? So now you just get this is f of xi plus gradient f of xi, comma, negative g plus beta over 2 times eta times g. All right. And if I take expectations of this whole thing is less than or equal to f of xi plus gradient f of xi, and maybe it should put it here. And the expectation of the gradient is the gradient. So I get something nice. Okay. All right. So the last thing that we need is from probability theory. So if Z is univariate, so we have that the variance is expectation of Z squared minus expectation of Z whole squared, right? And the same thing turns out to be true even for vector value randomness. Okay. So for example, if Y is vector valued, then variance of Y is expectation of norm of Y squared minus right. So just the natural extension of this formula to vector value things holds, where you just replace the square with the norm square. Okay. And you can prove this one coordinate at a time or all together at once. Either one would be fine. Okay. So if we use that, now we get expectation of G squared is going to be variance of G plus expectation of G norm squared. Okay. And we know this variance of G is at most sigma squared. That's the assumption. And the expectation of the estimator is just the gradient. So we just put that back in here, and then you follow through. I'm not going to do the fine-grained arithmetic, but you just have to substitute it in there, and we will get the formula. So the same calculations as before, except we have to take this one extra term into account. Right. So in the case of zero variance, we didn't have this term. This is what we did several lectures ago. Now we just have this extra sigma squared. And this is okay. All right, so we have this approximate monotonicity. And with the approximate monotonicity, you can really mimic the same analysis that we did a couple of lectures ago. Okay, so if you go back to the proof of gradient descent, we started out with this and this inequality. We added them up, simplified things, and got, several lectures ago, this expression, right? So instead of doing everything from scratch, what you can really do is really copy paste. The only thing that changed now is I have expectation on the left hand side, that's fine. But I have an additional eta sigma squared term, right? And that just goes through one step at a time. Okay. So we just follow through all of these calculations again, except we have an extra term here, which is this eta sigma squared by 2. Right? So let me not reinvent the wheel and just say, use the same calculations as for GD, but with approximate monotonicity. Okay. And if you do that, you get this natural analog where so in the case of gradient descent, we didn't have expectation, and this was the inequality that we started out with. But now we have expectations, and also we have this extra term. Okay, so this extra eta sigma squared is the only change from gradient descent. Okay. So what do you do with this? I'm just going to do the same thing, which is write this equation multiple times and add them all up. Okay, so we get x2, 1 and 2, x3, 2 and 3, xk plus 1, k plus 1. Okay. And just as before, if we add up all of these equations, we get some nice cancellations. So it's really just redoing the same things that we did before. So add up all equations and we get So the only thing is that we have this k plus 1 times eta sigma squared that is carrying over from the noise. And then we have the expectation on the left. All right. Okay. So this was where we were in even for gradient descent. And if I simplify this, I get very good. But here comes the trick. In the case of GD, when we had this average of function values, we were okay because it was monotone. And replacing everything just with the last one would only decrease it. So we were fine. In the case of SGD, it's no longer true that the function is not monotone. But what can help us here? Any guesses? Convexity, right? So remember, convexity told us that if I average, the function value on the average of 2 points is at most the average of the function on the 2 points, right? So if a function is convex, then f of x1 plus x2 by 2 is less than or equal to f of x1 plus f of x2 divided by 2. Okay. In fact, this is true in more generality. Okay, so you can, this is true even for 3 points, 4 points, and 5 points. And so for convex functions, in fact, you have that okay. So that's all. I mean, this was X bar that we defined, right? So you have to define the average. So this implies that the expected value of f of x bar is less than or equal to 1/2 eta times x0 minus x star squared divided by k plus 1 plus eta. Okay, so the exact bound that we were shooting. And of course, if I choose the minimum value, then also it's true because the minimum would be less than or equal to any one of them. Okay. Any questions about the analysis of SGD? The only change really came from using the estimator once, and then everything was fine.
Professor?
Yeah.
Yeah, for the proof, when we
1 second. You go ahead.
oh, sorry. Yeah, when we add all these equations together, I wonder where did f of x star go?
Oh, yes, you're right. Actually, that's important. So this is less than or equal to k plus 1 times f of x star. Thank you.
Thank you.
Thank you. Right, so this is thanks for pointing that out. We're actually comparing to f of x star always, right? That's our best optimism. Okay, what's your question? Oh, okay, perfect. Okay. All right. So, as I said, the analysis is similar, but it tells you that, you have to do something a little bit different. There are some special cases where people have analyzed what happens in SGD if I use the last iterate cell. These are called, this is called last iterate convergence bounds. And it's an active research topic because averaging everything is kind of is difficult to do and also seems a little bit lossy. Right? You ran it for 1,000 iterations. Do you really have to go all the way back? Do you have to average 10 things, 20 things, or can I guarantee the same bound for the last iterate itself? It's not true in full generality, but people have studied it and proved bounds in some cases. Okay. All right, and the other thing, that was asked before, let me say it again. Okay, so can you accelerate SGD? We cannot in full generality, but we can in some special cases, and we do that. And momentum is used. Okay, so momentum plus estimator is also used. And the only change would again be that wherever you were using gradient before, you would just use stochastic gradient. Okay. So for instance, if you wanted me to do like what's a heavy ball, stochastic heavy ball, let's say. This is stochastic heavy ball. You would say maybe something like xi plus 1 is xi minus, eta times your estimator plus some beta times the momentum term. Okay. It doesn't give you acceleration full generality, but you can still use it. Typically, you try to be more conservative here, but you can definitely run it. And it does give you boost in practice. No question about it. Okay. Any other questions? So as far as modern ML applications go, SGD is phenomenally important. I said because of the scale of things, that's what really gets used. You go through this epochs with different batch sizes and momentum parameters and so on. Okay. All right. So in the remaining time, let me say a few words about another very important practical tool called adaptive learning rates. It's a practical tool that is heavily motivated by theory. Okay. And in fact, it's a very nice story from the theory of optimization. And the idea here is, again, let's take the toy function that we looked at in the last lecture, which was something like, 0.1 times x1 squared plus, let's say I make it even worse and put 10 times x2 squared. Right? So now the gradient of this is 0.2 times x1, comma 20 times x2. Right? So the gradient is typically very big in the second coordinate compared to the first coordinate. So they're operating in completely different scales. Right? If I run gradient descent or even stochastic gradient descent, what happens? I would set xi plus 1 is xi minus this. Okay. So momentum can mitigate some of these things because what happens is, even if the gradient, even if the scales are different, as time goes along, the gradients can get added up and, it does go faster even along the narrow valley at some point. Okay. But still, it doesn't seem like the right solution, right? If you see this thing, what would you do first? I tell you, this is the exact convex function. I see the function. but you're still restricted to do gradient descent. What's the natural thing that you would like to do? Any sessions? Yeah. Yeah, right. Because, in some sense, you're basically saying, I'm measuring one in dollars and the other in thousands of dollars. Then what should you do? The units are not right, right? The units are not right. You have to somehow normalize. You have to make some kind of, the same unit, right? So one change in one coordinate is not the same as the same change in the other coordinate, but we're using the same step size, right? So you should adjust for that, okay? And this is called adaptive learning rates, meaning you can typically there are many things where you adapt for where you are. Maybe initially your step size is big. As you go deeper and deeper, the 1,000th step, maybe because you run 1,000 iterations, you tend to get more conservative. 1,000th step, maybe my eta is smaller than what I started at the beginning. Okay. But the other thing that you can do, and you should do, is adapt for the different scales that you observe. Okay. And this is where a method like AdaGrad comes in. Well, let me draw a big box. Well, okay. Okay, which is just short for adaptive gradient descent. Okay, so adaptive just means that I want my step size, aka learning rate, for each parameter. So adapt okay. So I am going to use different learning rates or step sizes, but I cannot do search now. Like here, it was okay for me to, maybe do hyperparameter search. Like I'll try it with eta equals 0.1. If it doesn't work, I'll try 0.01. If it works, then I'll maybe try 0.05 and do some kind of search like this, okay? But if I'm trying to do a different rate for different parameters, there's like a million parameters, I just cannot do independent search for everything, right? So what do I do then? So that's where an AdaGrad comes in. And the intuition is that somehow if your gradients are building up a lot in some coordinate, so here the magnitude of the gradients in the second coordinate is typically much higher than the magnitude of the gradients in the first coordinate. So intuitively, your step size should be smaller in the second coordinate compared to the first coordinate. Okay, so the change you see in the gradient is much smaller in the first coordinate. So I can take bigger steps. Right, so that's the intuition. And that's exactly what AdaGrad tries to do. And it does it by a simple sort of heuristic. It keeps track of what is the typical magnitude of the gradient that I'm seeing in a particular parameter. And I'll try and decrease my step size accordingly. All right. So let me write down that algorithm. It's a simple enough algorithm to write down. Okay, so start at x0 and okay. So this G0 is going to be our sort of the aggregate variance we've seen in the gradient so far. Okay, that's the way to interpret it. And once I write down the formula, it will be clear. Okay, so for each step I, what do you do? And, I'm going to write it straight away for stochastic gradient descent. It's defined for gradient descent, but whatever is defined for gradient descent, you can define for the stochastic version. Just replace the gradient with the estimator. Okay. So let's say G is the estimator for gradient f of xi minus 1, right? Now I'm going to compute Gi as for each coordinate. Oops. So in the jth coordinate, what is the total magnitude of the gradients that I've seen? Okay, that's what this is calculating. And of course, when you write it, you don't write it in this for loops. You would use vector arithmetic because that would be much, much faster on any hardware. Then you set xi of j is this would be the standard stochastic gradient descent update. I'm updating the new iteration as the old iteration minus eta times the gradient. Okay. The only change now is that this eta will get hit with a term that depends on the coordinate. Okay, it's some complicated looking formula, but there is some good intuition for why this is the right. It's saying, okay, in the jth coordinate, how much fluctuations have I seen in the gradient, and use the square root of that as a way to scale down the learning rate for that particular parameter. Okay. And just to deal with sort of borderline cases, maybe so far all of my gradients are 0, then I would be dividing by 0. I would never want that. So I just put some small epsilon, which is like some fixed parameter, like 0.0001 or something. Okay, does it make sense? So all we are doing is taking gradient descent, but we have individual learning rates for each coordinate that we are calculating. We cannot do a search anymore because we have millions of coordinates, millions of parameters, but they're calculated by this simple form. So if a coordinate has a lot of fluctuations in the gradient, then its step size is going to go down over time, right? So if I apply it, for example, for this function, what happens is in the second coordinate, these are growing as 400 times compared to the square is growing as 400 times compared to here. Right? So over time, the step size for the second coordinate would decay much faster than the first one. Right? So you're taking bigger steps in the first coordinate compared to the second coordinate. Qualitatively, it is doing what we want it to do. And it turns out this gives us the right. All right. So this is the key idea, parameter wise learning rates. Okay. Maybe let me not use epsilon. Let me just say alpha, where alpha is some fixed sort of, maybe 10 to the minus 3. Because I'm fixing so that I don't divide by 0. Right? Does it make sense? Simple enough heuristic, but it's quite useful.
Professor?
Yeah.
Yeah, I wonder what's the difference between capital G and lower G. Sorry, I'm a little bit confused on
So,
the
G is our estimator for the gradient. Okay. And
okay.
capital G is aggregating all of the different gradients that we've seen. It's the sum of squares of the gradients, more or less, in each coordinate.
Okay, got you. Thank you.
Okay. So, if my gradients are on the same scale in every coordinate, then, basically every coordinate will get hit with roughly the same factor. Nothing is changed. Whereas if they're on different scales, then the learning rates will start getting. Okay. So this is AdaGrad. And what we'll do next lecture is now we have AdaGrad, which takes care of this adaptivity, but it's not doing momentum. Right? So this AdaGrad has two problems. The first one is, I think, that it's still a little too conservative. So what happens here is over time, your step sizes become way too small because I'm looking at all of the squares of the gradients, right? In each coordinate, I'm adding them all up. So every time I add something and then the square root of this. Right? So over time, my step sizes might become too small. Okay. So instead of this, you can do something which is a bit more weighted average, meaning I don't have to add up the sum of squares of all of the previous 1,000 rounds. I'll have like an exponential decay so that I give more importance to things that I've just seen. Like the last 10 rounds should be more important in determining the step size for the next round than like, what I saw 1,000 rounds ago. Okay. So this exponential weighted thing shows up. That's called RMS prop. We'll talk about that in the next lecture. And then, of course, you can throw in momentum just because we can. Okay. And if you put adaptive learning rate plus momentum, you get something called ADAM, which is a phenomenally useful algorithm. And last I checked, apparently it is the most cited paper in ML. Okay. But the only thing it does is you take this update. And as we said, we can always do momentum, just put momentum. All right. We'll talk about that and a few other things in the next lecture. And then we'll move on to the next topic. Okay. So I'll see you all on Monday. And the first assignment will be out on Monday, just as a heads up.
Professor?
Yeah.
Oh, sorry. I have two more questions. First, for lower